Hi everyone, welcome to this lesson on using the trapezoidal rule to find the area underneath a function. So the trapezoidal rule looks a lot more complicated than the previous one, but we'll break it down step by step and we'll get there. So once again, I'm using as my example here, my function of x is 1 over x, a lovely straightforward function. I have a lower limit a, which is 1, and upper limit b, which is 6, so x equals 1 to 6. And again, I am using 10 small, I won't say rectangles this time, trapezoidal shapes. So what I want to do is calculate the width of each of these little trapezoids, and I want to calculate the area of each one. And I'm going to find the height of the function here on the left, the height of the function here on the right, and by joining a straight line between them, then I'm really finding the area of a trapezium. So for my area of a trapezium, remember, at least for this first one, if I call this area number 1 in my first little trapezium, then it would be, well, the width, w, and I would multiply that by, let's see, the left-hand edge here, that would be the function evaluated at the value of x0. The right-hand edge would be the function evaluated at x1, and then I would have to divide those by 2. That's my formula for the area of a trapezium. We find the average length of the two parallel sides and multiply by the width or the perpendicular distance between them. Now I would have to do that for each of these little rectangles all the way across, then add them all up. That would be quite doable. It would be a long, tedious process, so we take a few shorthand notations. Let's have a little bit more, just before we get too far into this, let's remember that the first value here is designated x0, this one x1, x2, and so on. In our case, where we've used 10 of these things, that one's x9 and the last one is x10. More generally, this would be xn minus 1 and this one would be xn. So let's, oh, what have we got some random scribble down there for? So let's have a look. Our trapezoidal rule tells us, let's have a go here. We would want to find the area as area 1 plus area 2 and so on, all the way up to area number n for the nth strip. And as we just saw, that's w multiplied by f of x0 plus the function evaluated at x1 over 2. My second one, same width. I would this time have the left-hand edge is x1, then I'd evaluate at x2, divide that by 2, and so on, all the way until I got to, sorry, forgot the w, until I had w multiplied by f of xn minus 1 plus f of xn over 2. Now I could factor w over 2 from this, and I would have f of x0. Now note here that f of x1 appears twice, so there would be 2 times f of x1, then there would be 2 of f evaluated at x2, all the way until I had 2 lots of f of x n minus 1, and finally f of xn appears just once. So the first and the last one appear only once. All of the intermediate ones are evaluated twice. And when we go back and look at that, that's because this edge here is involved in the calculation of both the first and the second strip. That's why it appears twice. Likewise, this one for the same reason. All of these ones appear twice in our calculation. but the very first and the very last one appear only once because they only appear in the very first and the very last trapezium. Now, there's a more compact way to write this. We write w over 2 f of x naught. All of these parts in the middle here, that's just a sum. We can put this as 2 times the sum of f of x I. And I would run from 1 to n minus 1. I goes from 1 to n minus 1. And we still have to add on f of xn at the end there. That's our trapezoidal rule. And that would give us an approximate area. Now, in our particular case, what are we dealing with here? Well, we had A equaled 1, we had B equaled 6, and we had N equaled 10. So the width of our strips, 6 take 1 over 10, comes to 0.5. Lovely. We probably should think about what x naught and xi and so forth are going to be. Well, let's go back here. X naught equals 1. x1 equals 1.5. x2 equals 2. All the way along, let's give myself a bit more space here, until I get to 5.5 and 6. So these are the bits here that I have to worry about in my summation. The x0 value of 1 and the x10 value of 6, they appear as separate parts of my formula. Let's do this. So the area is approximately, actually I might write the, whoops, what a mess. Try to fix that for you. There we go. I might write this as the integral from 1 to 6 of 1 over x dx is approximately given by the rule w over 2 f of x naught plus 2 times, it can't hurt to write the rule, f of x I. Remember, I started at 1 and finished at n minus 1. It's all of the intermediate ones. Plus f of x 10. Now let's get more specific with our case here. W is 0.5 divided by 2. I would have f of 1. My x naught value was 1. Plus 2 times the sum from I equaled 1 to 9 f of, now I'll have to think about that one in a moment, I'll come back to think about that, and then I have f of 6 because the last value of x was 6. Now what am I going to write in here? Remember, I have a counter variable that runs from 1 to 9 and I want to generate the numbers 1.5 to 5.5. My counter variable runs from 1 to 9. Each of them is stepping up in 0.5. So there's a good clue. It's going to be plus 1/2 I to show the incremental step. Now how would I get my first value of 1.5? Well, I start at 1, not 0 this time. So that's going to be half. I think it's going to be 1 plus half times I. When I equals 1, that generates the value 1.5, which is the one I need to start with. When I equaled 9, that would generate the value 5.5, and that's the one I need to finish with, 1.5 up to 5.5. So that's the tricky part of this formula. We have to think about that each time, depending on the circumstances that we're dealing with. Now it's time to get our calculator going, and we'll take a look at how we would operate this on the calculator. Let's just bring the calculator into the side there. So the first thing I need to do is pop over onto my graphing app and tell the calculator that the function we're dealing with is 1 over x, stored there in variable number 1. If I have a quick drawing of that, there it is, that's our graph. Now most of the work is going to happen back here on the Run Matrix menu. So I'll start to enter this, 0.5 over 2. Then a big giant set of brackets. Now when it has F1, I have to use the variable key, then the graph menu, graph submenu, and the graphing variable y1 is where I stored my function, and I'm using a value of 1 as my lower limit, plus 2. Now we'll pop back out to the maths menu, F4, and then find our sigma notation. Inside here we need an F. Remember on the calculator we use Y1. I'll give myself some little green brackets to work with there, and that's where I'm going to write 1 plus 1/2 I. Right arrow brings me down to here, where I can tell the calculator that I, in this case, ranges from 1 to 9. Now I need to add on F6. Close out that large brackets, and we're ready to go. I have 1.8115. Let's write that down. I have 1.8115 square units. That's not a bad approximation. So if I wanted to double check that, underneath the maths menu here, we can do an integral of our function 1 over x ranging from 1 to 6, and we get 1.79. It's a pretty close approximation. This trapezoidal rule is not too bad. Now, if of course, like any of these techniques, if we wanted to increase the accuracy, we would simply use a larger number of trapezia. We would not have n equals 10, we'd say 100 or 500. And as long as we just make a few small adjustments here and here, we would still have really not that much harder calculation to deal with, and we would end up getting a much more accurate answer. That's it for the end of this video. Thanks for watching. Next one is going to be about Simpson's rule.